Welcome to the fourth lecture in the continuation of the series about stars. And in this particular presentation, I am going to be talking about why the stars the way they are. Why do they appear the way they appear? And what really sustains them in this universe? This lecture is followed after three lectures, and I hope the listeners have watched those lectures because in order to have a more better understanding you will need to watch them and take out some time and watch those, and if you find any mistakes to comment and I will try to improve myself as well. So another thing that I would want the listeners to have is a pen and a paper. Keep a pen and a paper along with you because in this particular lecture I would be showing equations that are not very difficult, but still they are a bit complicated. So note them down, visualize them, and try to understand how they function inside the star and keep it from collapsing. So as we can see here on this slide, uh, the upper left corner, or maybe the right corner for you, what do we see? We see this cluster of galaxies, and these little dots are also galaxies, which contains billions of stars. It is a very detailed image taken by the Hubble Ultra Deep Field Telescope. We have more refined images coming from the James Webb Space Telescope, which was launched a few years back. We have the Andromeda Galaxy M31. We have the Carina Nebula here, and it is the nursery for the stars that get born out of it. Most of them are protostars and they become large stars, stars similar to our sun, much smaller stars, and at the end of their life, neutron stars, white dwarfs, and the enigmatic black holes. So, these gas clouds are also a very important part of our universe because they are the nurseries, the first places where these stars are created. And because these stars get created, we human beings get created because everything that we are made of is inside these little stars, which finally comes out and becomes matter. Matter like us that can talk and that can imagine. We have the Crab Nebula underneath, and we can see the star remnants of an exploded star. You can see these gamma rays and these infrared rays. These are all colored in different spectrums, and these are different elements we can visualize here that came out from the star's explosion. It going to supernova. We have the Ring Nebula here, M57, and we have many more structures in the universe that define a star. I hope you research about them, you generate an interest inside you, so that when you look up in the night sky and see those little dots, you have a better understanding about them, and it can help your intellect to grow. Going to the next slide. In this slide, we're going to discuss about Sir Arthur Eddington. So he was a monumental figure in the 20th century astrophysics and was best known for his work on the internal structure of these stars that we see in the sky. And he played a very pivotal role in proving the general theory of relativity that was published in 1915 by one and only Mr. Einstein. So this guy had a great role to play in the scientific world in the early 20th century. So let's discuss about his key contributions to science in general, stellar science in general, the theory of stellar structure, the radiation pressure, the hydrostatic equilibrium, and as we have discussed, the 1919 solar eclipse that proved the Einstein's GTR. So, the theory of stellar structure as per Eddington was that stars are stable because the inward pull of gravity that tries to bring the material of the star towards the core, trying to force it to collapse and explode, therefore, it is perfectly balanced by the combined pressure of gas and radiation. So you have to remember this particular line. It's very important and it will be further discussed in the next slides. And it was a very revolutionary insight into how the stars function. Eddington gave a new insight and told us about radiation pressure. He introduced it as a critical physical force in maintaining a star's stability and is directly related to his theory of stellar structure. We have already discussed the hydrostatic equilibrium in the previous videos, and Arthur Eddington he formalized the state equations relating the star's pressure density that varies along its structure and the temperature gradients that are very different along different layers of the star with the star's interior. So these three are important components of his theories, and then his experimental observation of the GTR that he did by observing and measuring stars shifting near the sun's limb and therefore proving that Einstein's general theory of relativity is the right description about gravity. So we go on to the next slide and we can see here a book. This book, The Internal Constitution of the Stars, was written by Sir Arthur Eddington and it is the foundational book for studying the stellar physics, and you can consider it as a classic in that particular stream because the ideas that Arthur Eddington proposed in this book were the foundational ideas for developing stellar physics further on into the late 20th century and the mid 20th century. So his insights in this book are very uh, true and experimentally verified to some extent and give a better description about the stars. And why is it so will be discussed now. Well, you can also buy the book on Amazon if you want to. So, what was the Eddington's theory of stars? So, Sir Arthur Eddington's theory, primarily detailed in his 1926 work, that book that he wrote, which I showed you in the previous slide, and it provided the complete physical model of how these stars in the universe function and why they remain stable despite the immense gravitational pressure of the core. So, what was the thing that he really proposed? So, he proposed that a star is a giant sphere of gas, which it is because it is made out of a giant gas cloud. So, obviously, it has to be a giant sphere of gas. And this giant sphere of gas is in a constant equilibrium state. So his argument was that this inward pull of gravity of a star that tries to pull the matter inside towards the core, trying to collapse the star, it is perfectly countered by the outward pressure of the radiation and the gas of the star. So, why is it so? Is it because the core creates temperatures and pressures that are too high, that that then creates radiation, and radiation has pressure, inherent pressure, which prevents the star from collapsing? And there are other elements to it as well. The gas pressure, which is because of the constant movement of the free electrons and protons inside the plasma state of the core, which again interferes with the collapse. So his point was that all these forces prevent the star from collapsing. His essential new physics was the realization that massive stars, which are much larger than the Sun, have an additional pressure, which is the radiation pressure, the force exerted by photons escaping from the core, which is in combination with the gas pressure, and therefore both these forces prevent the star from collapsing against the gravity. So, radiation pressure was his insight, which the scientists before him didn't have. They only considered the gas pressure due to the kinetic motion of the free electrons and other molecules inside the star. So, this was a shift in the understanding, and it was a very necessary shift, or else our understanding would have had a wall in front of us where we would not understand the stellar objects in its full scale as we do now. So in this slide, we are gonna take a case of a tiny, rather infinitesimal cylindrical element, which is inside the core where the fusion is taking place. So our main purpose is to keep the star stable, to avoid it from blowing away or collapsing within itself. So we have to maintain that each element inside the star, which it is composed of, also remains in equilibrium. So by taking this cylindrical element as an example, we can see that it is stable when all the forces that act upon it are balanced out. And we see that the primary forces acting upon the cylindrical element are the pressure differential force against the gravitational force that is applied on the cylindrical element by the mass interior to it. So these two forces that are acting on this cylinder, one being the gravity due to the mass interior to it, and the pressure differential force due to the different pressures across its width, they have to balance themselves out so that the element don't move or don't blow away or go right out of the star or collapse into the star. So first we have to define the mass of the cylindrical element. So how will we define the mass? We know that mass is the density times the volume of the cylindrical element. And considering the density to be a function of the radius or the radial distance from the core of the star, from the center of the star, we know that the mass of the cylindrical element would be the density, which is a function of the radial distance from the center, times the volume of this cylindrical element. We take the cross-sectional area of this particular cylindrical element to be 1 square units. Therefore, its volume would be 1 times the width of the cylindrical element, which is dr. 1 times this width. We get the entire volume because you're running towards this direction. So you get the entire volume. So the mass would be density times dr. Now the gravitational force acting on this element is given from the Newton's law, which is G, gravitational constant, times the mass interior to the cylindrical element, mr, which is here, mr, times rho r dr, which is the mass of the cylindrical element, upon divided by r squared, which is the radial distance from the center of the cylindrical element. We don't take it as r plus dr because it doesn't make any big difference. So pressure is defined as force divided by area. So since the area of cross section on which the pressure is acting is 1, therefore pressure is here equal to the force divided by 1. So the force is equal to gm rho r dr by r square, which is equal to the pressure as well. So we take the dr underneath the pressure differential, and we get the hydrostatic equilibrium equation for the star, which is a differential equation. And it's a very beautiful equation, and you can see r is the radius from the star center, pr is the pressure at the point r, because pressure is also varying inside the structure of the star, and the temperature is also varying. There are many kinds of different gradients here. So what are the key interpretations and physics? So this negative sign indicates that the pressure decreases as we go outwards outside from the core, as you move away from the core. This is the pressure gradient, which is the outward force per unit area. So this is the gravitational pull per unit volume. It is the inward force. So the outward pressure gradient perfectly balances the inward gravitational pull of the star's core, ensuring that the star doesn't collapse or explode. If this equation is violated, it will lead to an unstable star which is prone to explosion or collapse. So I hope you understood this slide. In this slide we have the Boyle's law that actually defines the pressure of an ideal gas with respect to the temperature of the gas. So you can see the equation here, P is equal to N times K subscript P times T. N is the number density, that is how many molecules or particles are there per unit volume. So you can imagine as the sun contracts and its volume increases, the N goes up because there are more particles in less volume. Therefore the pressure goes up, and therefore the temperature also goes up. So Kb is the Boltzmann constant. It's a fundamental constant, and its value you can see here, 1.38 into 10 to the power minus 23 joule per Kelvin, and it relates the average kinetic energy of the particles in the gas with the thermodynamic temperature. Actually it's a constant, it's a proportionality constant, and its value is this. T is the absolute temperature of the gas. Higher the temperature, more faster the particles will move, therefore higher will be the pressure. So this equation is a kind of meter for the star. If it increases the temperature, the pressure will also increase. If we go further out into the star where the temperature is less, the pressure will be less, and the number density will also vary. Now you might think, why this equation which pertains to the ideal gas? Ideal gas is an ideal situation where stochastic effects of the gas molecules are ideal. They are not they are averaged out. They are not random. Even if they are random, we have an average prediction, and we can say, yeah, this is how the gas is behaving. Why does this why is this principle valid inside a star? So what happens is that we consider two situations inside the star, which is the small scale situation and the uniformity situation. So when we take little parts of the star, what we observe is that in these tiny parts, the temperature is not changing that much as it is changing, say, from the surface of the star to the core of the star. It is very uh, similar if we consider a tiny parcel from top to the bottom. So the temperature gradients are effectively zero. Therefore, because the temperature gradients are effectively zero, it is behaving as an isothermal environment. Therefore, ideal gas prefers an isothermal environment, and we have the Boyle's law being followed. Also, there is uniformity. On this microscopic scale, the gas is behaving like an ideal gas at this constant temperature. This assumption of the temperature not varying within small regions of the star. So, using all these principles and these approximations, we know that gas, because star is made up of gas, it behaves like an ideal gas, and therefore it follows the Boyle's law. It is a very important equation as terms as stellar physics is considered, and we will be using it further on. So what do we have with us? So we have two equations that we just saw. The first is the hydrostatic equilibrium equation. The pressure gradient is equal to the negative of the gravitational constant multiplied by the mass interior to the element, the cylindrical element, and the density, which is a variable density according to the radial distance from the center divided by the distance from the center squared. It is an important equation because it keeps the star from collapsing or exploding. And the other equation is the ideal gas equation, Boyle's law, which we just saw. Where is n? So n is actually this quantity. So n is equal to gas density at radius r divided by the mean molecular mass of the gas particles. So higher the temperature, therefore higher the density of the particles, the number density, and therefore higher will be the pressure. So you see how things are going on. So when Sir Arthur Eddington came into the picture, so what was his insight that really shook stellar physics and created a new kind of way of seeing things? So what he basically did was is that he said that stars are globes of gas, as we know that, in which the inward pull of gravity is balanced by the combination of the gas pressure and the radiation pressure. So his essential new physics was radiation pressure, and we discussed it in the second slide. So we can see we have the total pressure is now defined as the gas pressure plus the radiation pressure. This is the total pressure we have now. So What is the value of the radiation pressure? It is defined by this formula. P radiation is equal to 1 by 3 times the Stefan's constant into the temperature raised to the power 4. So you can see the value of the Stefan's constant and how it is related to the Stefan-Boltzmann constant, and we can see and we can calculate the radiation pressure of a star if we know its temperature, because A is a constant. So because there are different temperature gradients, each region of the star is having a different radiation pressure, but this difference is also responsible for keeping the star stable. So what is this A also? It's also called the Stefan's constant or the radiation density constant, or simply the radiation constant. The Stefan-Boltzmann constant, it represents the proportionality between the total energy radiated per unit surface of a black body, and it is related to the fourth power of the thermodynamic temperature of the black body. Now you might ask me, what is a black body and how did this equation came to be, and how did we find the Stefan-Boltzmann constant? I hope you will research it yourself, because it's an interesting concept, and the entire quantum physics developed because of the black body concept. So it is a good assignment for you guys. I hope you will try to learn about black bodies yourself, and do comment what you have studied. So what is radiation pressure? It is basically the outward pressure exerted by the photons that emerge out of the core due to the fusion process, or as a result of the fusion process. And since the radiation pressure is proportional to the temperature raised to the power 4, as we can see here, it's the temperature raised to the power 4. Even a small increase in the core temperature, for example, if you go from 10 million Kelvin to 11 million Kelvin, it's not small, but in terms of the stellar uh, quantities, it's small. So if you go from 10 million Kelvin to 11 million Kelvins, there will be a significant outward pressure exerted by the photons that get generated through the fusion process, and it can create a problem for the star, because it doesn't want the pressure gradients to change significantly, or else it will just burst, it will go supernova, it will explode. So the essential new physics, as you might have got a brief or a maybe small idea that was introduced by Arthur Eddington, was that we have two primary pressure gradients that are acting on the star's core, which is the gas pressure and the radiation pressure. You can see here the core of the star and how the gravity is pulling the material inside, which is being prevented from the radiation pressure and the gas pressure as well. Yes, different regions of the star. It is our sun. We have the corona, we have the magnetic field lines going out, we have the photosphere, we have the chromosphere, we have the corona. You can also study about the different parts of the star and how these magnetic fields get created, and why also the solar storms get created, which are also related to the magnetic field of the star. Its magnetic field keeps changing also due to the convective effects inside the convective zone of the star, due to the plasma moving around and the free electrons that are also moving around haphazardly. So to study about them too, this field is called magnetohydrodynamics. So yeah, if you are interested, you can read about it. In the previous slide, you might be interested in knowing why this 1 by 3 in the formula of the radiation pressure. So, as we know, in the three-dimensional space, energy has to spread out equally in all directions, and therefore in the XYZ directions primarily, we have in total three parts. It's a trio. So pressure on the surface is always perpendicular, calculated in the direction that is perpendicular to the surface. So we here consider the x component of the pressure to be always perpendicular to the star's surface or the star's element in which we want the equilibrium to be maintained. So therefore we divide the total radiation pressure coming out in all going out in all directions, which is a times 10 to the power 4 by 3, to find the perpendicular component of the radiation pressure, which is actually the pressure we require when we are defining the state equations for the star. So we imagine that the photons are hitting the surface of the star, and because they move in all directions in the spatial dimensions, therefore they have a way of moving which is called the isotropic motion. So photon is an electromagnetic radiation, and if a radiation transfer energy to a particle, it also has to transfer momentum. But photon doesn't have a mass, but momentum was defined for something that has mass. So what is this photon momentum? So all this came out from Einstein's special theory of relativity, and it states that also Maxwell's equations. So what it states that the wave has a momentum and an associated energy, and how they are related, it is related by this formula. It states that the momentum is equal to the energy of the wave divided by the speed of light. So energy of an electromagnetic radiation depends on its frequency mu, which gives h mu divided by c, and therefore we get h by lambda, where lambda is the wavelength of the electromagnetic wave. So the inherent momentum inside a electromagnetic wave is given by the Planck's constant divided by the wavelength of the wave. So the momentum for a visible photon, that is inside the visible spectrum of the entire spectrum, is 10 to the power minus 27 kilogram meter per second. This is the dimension of momentum. So this much momentum is being transferred by a photon to anything that it interacts, and it depends on the kind of collision it is. It can be an elastic collision, or it can be an inelastic collision. So therefore the energy that gets transferred or the momentum gets transferred, it also varies accordingly. So I hope you understood the concept of momentum, and especially the photon momentum, and what is its implications inside the star, we will see now. So we have to define two new terms. The first is luminosity and the other one is flux, because these two terms are going to be very important and fundamental in defining the star's main equations of luminosity and the mass luminosity relation. So what is luminosity and flux? Luminosity is actually the measure of the total amount of energy any object emits per unit time, and in astronomy we will consider the object to be a star or a celestial body or a galaxy or a planet or an asteroid if it emits energy. So for a source with luminosity L, that means for a source that is emitting energy, an amount of energy per unit time, the energy crossing per unit area per unit time. That means the energy that is crossing per unit time, which is the luminosity, that is the luminosity divided by the area, which is the flux, is defined as follows. So flux is defined as luminosity divided by the area through which it is spreading. Because it is spreading over a sphere, the area is considered to be the area of a sphere, because the spreading out is isotropic. Isotropic means it is spreading out equally in all directions. So it will take a form of a sphere. It will take the form of a sphere as it spreads out. And this sphere's area depends on the radial distance from where it is spreading out. It's 4 pi r square. So we understood what is flux. Flux is the luminosity divided by the area of spread, where luminosity is actually the energy emitted by the object per unit time. So flux has the dimensions of joule per unit area, that is meter square, per unit time, that is second. So joule per meter square second. So you understood what is flux. If you understood it, we now define the momentum flux. So the momentum flux per unit area is simply the flux divided by the speed of light. So it is actually a force. Now, why it is a force? It is a force because when we multiply it with the scattering, Thomson scattering cross section, the area components go away. Luminosity is actually energy per unit time. So energy per unit time, so time is here, time times velocity is distance, so energy upon distance is actually force, because energy is force times the distance. It is the work, how much work is done by the force, and its energy, or its energy. So we have the force here. So momentum flux per unit area is this, luminosity divided by 4 pi r square c. So we know that electron doesn't absorb all the radiation that falls upon it. And in the previous lecture about Thomson scattering, we discussed it in depth, and therefore we get to know about the cross section which actually interacts with this photon, and it comes out to be a constant, which is sigma t, the Thomson scattering cross section constant. So the force on one electron is this. So you have to remember this. It's a good formula, and it will come handy. So we get it, and flux is the amount of energy, that is the luminosity per unit time, passing through a unit area at a specific distance. Because luminosity actually is not dependent upon the surface area of the spread. It is equal in all directions. It is equally the total energy the star emits in all directions, whereas the flux, because the flux has the component of the area, as we go further away from the star or from the emitting body, the flux keeps reducing by the inverse square law. So you can see here L is the total luminosity, and the flux is proportional to the inversely proportional to the distance squared. So you can see for this much area we have this much flux, we have for this much area we have less flux, and here for much less flux. So there's also one more thing is that flux is what we actually measure here on Earth with a telescope, not luminosity. It is through this flux that we measure the luminosity using these formulas. So here we have a rectangular slab. So we imagine a incoming flux F that is, coming into the slab and then moving out. So we consider the cross-sectional area of this slab to be 1 square unit, its thickness that interacts with this flux to be dx, and its density to be rho, and one more extra term which we are going to define as mass absorption coefficient per gram kappa. So the fraction of this incoming flux that gets absorbed by this slab is equal to this F kappa rho dx, where rho dx is actually the mass of the slab, because 1 times dx is the volume, density into volume is actually the mass. So kappa into mass will give us a term that doesn't have any units because it's per gram, and mass by mass from the denominator will cancel the mass unit from the numerator, and will end up with the flux that gets absorbed by the elementary slab. So this is an important relation. Now since we know the flux absorbed, we also know the x component of momentum absorbed. Momentum is simply the flux divided by the speed of light, but it is per second. Momentum absorbed per second by the slab is given by F kappa rho dx upon C. You have to consider one assumption is that if this flux, here the flux is coming straight towards the rectangular slab, if it was coming at an angle, also it will have the same value. Why? You have to research about it. Why it will have the same value even if the incoming flux is at an angle to the rectangular slab. It's not always possible that the flux will be perpendicular to the slab, but why it is possible? Because we consider our element to be in the perpendicular direction. There are other reasons also, you can look them up. So the outgoing flux is simply the total flux that was coming in minus the flux that has been absorbed, which is F kappa rho dx. So Newton's second law, as we know, is that it states that the force is actually the rate of change of momentum. So dF is equal to d rho by dt, which is the rate of change of momentum. Because this particular rectangular slab is constantly absorbing momentum from those photons, or due to that incoming flux every second, the radiation is actually applying a continuous physical force to the slab. So you agree with me, because this particular element is actually absorbing the momentum that is transferred to it through those photons. Therefore it is uh, also being applied with a continuous force, which comes out from the Newton's second law, and the relation is as follows. So by definition we know that pressure is force divided by area, and since our slab doesn't have a cross-sectional area, it is 1 square units. Therefore numerically the pressure is equal to the force. So we can simply write it as the radiation pressure is the flux divided by the speed of light, the momentum absorbed by the slab per second per area. So force applied by the absorbed radiation is exactly equal to the difference in radiation pressure across the slab. So you understood this particular aspect, the this one. So we can also do it using the units, because flux is actually energy per unit time per unit area. So for this is energy per unit time into speed, which is distance. So for energy per unit distance into area, which will be energy per unit volume. Now pressure is force upon area, and energy is force into distance. Force into distance upon volume is force upon area. So it has the units of the pressure. I hope you are having a pen and a paper so that you can understand the units and why they match up, because it's very important you don't feel confused. So it's simply the pressure is equal to the flux divided by the speed of light. We calculated the flux to be F kappa rho dx. We put it in and we get the relation that we see here. F kappa rho dx upon C is the radiation pressure. So if this slab is inside a star, if this rectangular slab is inside a star, for it to be in radiative equilibrium, momentum gained per second, the momentum gained per second by this slab must be fully absorbed by the matter contained inside the slab, so that the star does not blow itself apart. This is a huge insight or relation, because if the slab is absorbing too much and the incoming photon pressure or the momentum being absorbed cannot equal the radiation pressure, what will happen is that this slab will just blow apart, will move outside the star. So for slab has to stay in hydrostatic equilibrium, it has to maintain this equation as well. So we get the precise differential across the slab, and it is here. The total outward pressure is actually the combination of the gas pressure and the radiation pressure, as told by Mr. Arthur Eddington. So we write the differential equation, which is the gas pressure plus the radiation pressure, and it is this equation is what supports the slab against gravity. Now we assume a hot massive star, a red giant star, much larger than the sun. We assume that there is no gas pressure because the radiation pressure is too dominant, and the gas pressure becomes negligible. Therefore we say the star is in purely radiative equilibrium. It is in purely radiative equilibrium. So in a purely radiative equilibrium state, we have three governing equations. So one is the hydrostatic equilibrium equation, as we know, as we have discussed. Another is the radiative pressure gradient, F kappa rho C, and we have discussed it as well. Remember, we took the dr here, therefore it's the pressure gradient as we move inside the structure of the star. And we have the flux luminosity relation, which is simply flux is equal to the luminosity divided by the spread area. So one more insight you should know is that in stellar physics, the stars where radiation pressure dominates over gas pressure are the most massive and hottest stars in the universe, and they are typically greater than 10 to 50 times the mass of our sun. So in these cases only, we are going to assume that the gas pressure is negligible, and these equations will hold valid for these massive stars. Going on, we see is that after dividing the equations there in the previous slide, which 1 and 2 equations, the first being the hydrostatic equilibrium equation, the pressure gradient equal to minus gm rho divided by r square, by the second equation, which is the equation of dp total divided by dr is equal to f kappa rho c, f kappa rho divided by c. So when we divide these two equations, and assuming that the total pressure is contributed entirely by the radiation pressure, we get 1 on one side, and we get a relation from which we extract the luminosity to be this 4 pi g m c upon k. Okay, this is one equation. So deep inside a hot massive star, this hydrogen is completely ionized, and there is a plasma-like condition where free electrons are floating around. The protons are also floating around, that is hydrogen nucleus is floating around. So this means that the atom is split into its constituent particles. One heavy proton, which contains nearly all the mass because it is much heavier than the electron, which is very tiny, and one incredibly light electron. Even though these electrons are separated by the intense heat and pressure of the star, they are still, they are still held together by the strong electromagnetic attraction. So we have to look at the forces that these two subelementary particles are facing. So since this proton is actually 1836 times heavier than this tiny electron, so gravity is almost ignorant for the electron. It doesn't care for it. It is we are assuming all these things. There is a value for the gravitational force as experienced by the electron, but it is very small compared to that uh, you know that is on a proton, and therefore we consider it to be nil, and therefore the entire gravitational force pulls directly downwards on the mass of the proton, which we will define as m subscript capital H. So the inward gravitational force on the proton is gm1, which is the mass interior to the proton and the mass of the proton itself, divided by r squared, the distance of the proton from the center of the star. So light or the photons that are rushing out from the core, it carries momentum, and the force experienced by a single electron, as we discussed earlier, is this L by 4 pi r square c into the Thomson scattering constant. And if you want to confirm, you can go back and see as you replay the video. So what we do is that we equate both of these equations because we have to balance everything out. The gravity is pulling the protons inside, and there's this outward radiation force on the electron and therefore on everything inside, because these photons are usually not interacting with the protons. And there are some correction factors in these equations, but still we are considering situations that are easy to understand. to start building a foundation in stellar physics. So we compare them and we get L to be 4 pi gc m times small m subscript capital H divided by the Thomson scattering constant. So we are going to compare this with the equation A, which was 4 pi g cm upon k kappa, the mass absorption coefficient per gram. So we understand that kappa, the mass absorption coefficient, which is also the opacity of the star, is defined as the Thomson scattering constant divided by the mass of the proton or the hydrogen nucleus. But this equation holds valid only for hydrogen dominant stars, where hydrogen is abundant, like huge stars where hydrogen is abundant, or the star is purely made of pure hydrogen. So you get the insight, I think, here. Now we will move on. So using the principles of this radiative equilibrium, Eddington derived the maximum possible luminosity a star can have, which we will, say it to be the Eddington limit, the Eddington luminosity limit, which is equal to, as we have already seen, 4 pi gcm divided by the mass absorption coefficient, or the opacity of the star, is equal to 4 pi gcm times the mass of the proton divided by the Thomson scattering constant. So what is the insight that we get from this formula? 4 pi is a constant, the gravitational constant is a constant, the speed of light is a constant, the mass of a proton is a constant, the Thomson scattering is also fortunately a constant. So what remains that is not constant? It is the capital M, the mass of the star. Therefore, the Eddington limit, luminosity limit, is directly proportional, and it is solely determined by the mass of the star M. So if the if the luminosity of the star is less than the Eddington limit, the outward radiation pressure, it will balance out the inward gravitational force, the outward net radiation pressure, and therefore we will have a star that is stable. But if the luminosity is greater than, if it exceeds the Eddington limit, what will happen is that these pressure forces will win. It will surpass the gravitational attractive forces, and the plasma inside the star will blow away. It will explode. Therefore, this Eddington luminosity limit is a very important relation, because it determines why and what stars are gonna exist in the universe. You can see in the diagram also, if the luminosity exceeds the Eddington luminosity limit, what will be the fate of the star? So we will take one more case. We will consider an imaginary surface of radius r, and we will determine the luminosity that is crossing this imaginary surface. So going back to the radiation pressure equation, we know the radiation pressure to be F kappa rho dx by C. So we also know that it was equal to 1/3 times the Stephen's constant times the temperature raised to the power 4. After doing a differential of it, we get this particular term. Because temperature is varying, we don't differentiate it. It is a variable. Therefore, if we compare these two equations, one of this and this, we get this. F is equal to the flux is equal to minus A times C upon 3 kappa rho into the D times the differential of temperature raised to the power 4 divided by the differential of the radius or the distance from the center of the star. Now we know the luminosity is flux times the cross-sectional area over which the energy is spreading. Therefore, we get the luminosity relation also, which is the previous equation multiplied by 4 pi r square. Here we have not used dx. You might get confused. It's dr. It's for a star basically. It's the radial distance from the core. So we get the equation of radiative equilibrium. So what does this formula state? It states that if we know the temperature gradient, which is this quantity, and the opacity, kappa, the mass absorption coefficient per gram, we can predict the luminosity of the star. So from the results on the left hand side, we will do some scaling relations. We will do some proportionality relations. So luminosity here we can see it is all these are constants, okay, and this also and this is a constant. So its temperature raised to the power 4 r raised to the power 4. Why? Because here the radius will cancel out 1, so it will remain 1 to the power, and density is mass upon volume, that is mass upon radius cubed. That radius cubed will go here, it will be 1 plus 3, therefore r to the power 4 and divided by the mass. So we get from this, we get here, that is luminosity is proportional to r times t, both to the raised power 4 divided by the mass. Now considering only gas pressure, and we have the Boyle's law and the ideal gas equation, which is the pressure is equal to rho kT, where rho is the density and T is the absolute temperature. And we also know the hydrostatic equilibrium equation, which is the pressure gradient is equal to G m rho by r square. So we compare, what we do is that we will substitute this pressure here. So rho kt, k is a constant, opacity is a constant. Considering it to be a constant for a star, we get rho t by r is proportional to m rho by r square. G is also a constant, so it also cancels out and we get a proportionality relation. So here also cancelling the densities, considering them to be constant over large scales, we get RT is proportional to M. Now substituting RT as M in this equation, we simply get L is proportional to M cube. Now this was a huge result which Sir Arthur Eddington found, and this is the mass luminosity relation. And when Arthur Eddington in those times matched with the available data of the stars, he found that it fit very well. There was this curve of luminosity and mass, and it was found to be very close to the cubic curve. So it was a great finding. Now you understand what the significance of this equation is, that the luminosity comes out to proportional to the mass cubed. So more the mass of the sun or the star, the more is its luminosity. Therefore larger stars will have more luminosity. But is this relation always valid? We will see it in the next slide. So modern data, the data that we have right now of this relation, this mass luminosity relation, is not like a constant. It's not like the mass raised to the power 3, it's always there. Like for example, for very low mass stars, in real stars, in very low mass stars, which is that the mass is less than 0.43 the solar mass, the luminosity is proportional to the mass raised to the power 2.3. So why does this happen? It is because the opacity, it is varying, the density, it is varying. Therefore this relation will not be ideal. It will also change as the mass changes. So it is like a feedback loop. The mass changes, the luminosity relation also changes. So these stars, these low mass stars, are primarily called red dwarf stars. They are relatively cool. Their interiors, they are perfectly and completely convective. So this means that the energy that is transported outside the star, it is completely because of the physical boiling motion of the plasma rather than the radiation. So the dominant source of resistance to light that comes out of this red dwarf star is from these negative hydrogen ions. These negative hydrogen ions inside the plasma, and their energy is generated exclusively via the slow proton-proton chain reaction that I am going to discuss in the next lecture. Uh, the combination of this convection and these negative hydrogen ion pressure creates a opacity. The opacity, this opacity is different for different mass stars, and therefore it creates a shallower scaling curve. Why it's shallower? Because the exponent is 2.3. It's not large. All these are red dwarf stars. You can see here VB10, Proxima Centauri, Barnard star, Wolf 359, Tegarden star. We have the Ross 128, Kepler 138, even Jupiter. So all these red dwarf stars have this mass luminosity relation. For intermediate mass stars, that is their mass being in this range, less than 15 solar masses and greater than 0.43 solar masses, the mass luminosity relation is this, which is raised to the power 3.5 going up to 4. So this intermediate mass star regime, it includes our sun, and it also extends to much and even much brighter stars. So here radiation has a good role to play, and the opacity is governed by the Cramer's law. I think you should study about Cramer's law by yourself, uh, because here photons scatter off electrons in heavy elements. So these stars core also have carbon and magnesium, silicon, even it can go up to iron in certain situations when the star is in its death stage. So due to these heavy elements and the electrons that are bound to these elements, there is some scattering of the photons. Therefore, the scaling relation also varies. And also this opacity is highly sensitive to internal temperature and density gradients of the star. It heavily influences the energy flow from inside the star to the interstellar space, and it leads to the steepening of the exponent relation significantly. So, but at the higher end of this relation, where the mass approaches the higher figures, which is the 15 solar masses, so the reaction, the chain reaction, the PP chain reaction, which was slow, it goes to the higher temperature sensitive carbon nitrogen oxygen chain reaction. So it pushes the exponent closer to 4. Therefore, when it goes to higher temperature sensitive CNO reaction, the luminosity also increases because there are more temperature, more fusion, therefore more high energy gamma photons being released from inside the core. For high mass stars, which is like lying in this range from 15 solar masses to 50 solar masses, the luminosity is proportional to the mass cubed that Arthur Eddington found, because we assumed that radiation pressure was dominant and we neglected the gas pressure. Therefore, we came to this relation. So opacity is no longer dependent here upon temperature, because photons, they are exclusively bouncing off due to the Thomson scattering principle, and the entire core is completely ionized and its temperatures are very extreme. Uh, so Arthur Eddington basically discovered this model, and this is what he gave as the mass luminosity relation when he discovered it. There are even ultramassive stars which are greater than the 50 solar masses, and here simply the luminosity is proportional to the mass of the star. So, as the star approaches the Eddington limit, the immense output of high energy photons generates a radiation pressure that completely eclipses the standard thermal gas pressure. Here also, we neglect the gas pressure values in our derivations, and in this extreme state, the outward push of photons is so dominant. I mean, it is so powerful that even if we add more mass, the luminosity relation will only increase linearly. So we can see what it shows is that we can't keep going on and increasing the mass indefinitely. That means there will come a time when the mass will have to stop increasing, or else the star will blow apart. So in order to get that limit, we have the Chandrasekhar limit. This is the Hertzsprung-Russell diagram. Here we can see the smaller stars, less than 0.43 solar masses. The white dwarfs here lying, their luminosity is in this range, much less than the main sequence in which even our sun is interspersed, and sun-like stars and till up to 15 solar masses, and these are supergiants which is up to 50 solar masses, and much larger these are giants and these are supergiants much larger than the 50 solar masses. And we can see how the temperature is increasing in this direction, and the luminosity is also here. The luminosity for the supergiants will increase linearly. So here we will be calculating the stellar lifetimes, and we will keep the Chandrasekhar limit aside for some while. So, well, we are gonna live up to some age. What determines our age? It is determined by how much our cells can sustain the oxidative stress. The mitochondria in our cells can, remove those oxidants from our cells and therefore keep the cells alive in different organs of our body. So this is the limit that we have in this on this planet, in this universe, as being creatures that are alive. So actually we have fuel inside our bodies. Even if we don't eat, then also we are gonna live up to a few days or something. So a star also has a lifetime, and it is proportional to the amount of nuclear fuel it has. And it's obvious, if it has more fuel, it will live for a longer time. If it has less fuel, it will live for a lesser time. But there is a caveat. So we will see why that is so. So basically the star's lifetime will be calculated by the amount of fuel, that is the mass of the star divided by its luminosity, that is how much energy it is radiating per unit time. So what is the final relation? Considering the luminosity to be proportional to raised to the power 3.5 for an intermediate star like our sun, we get the lifetime span to be m raised to the power negative of 2.5. So what does this negative exponent mean here? It means that the more massive a star is, drastically shorter its life will be. Amazing. So, for example, let's take a star with 10 solar masses. So, it will not live 10 times the life which our sun is going to live. Our sun is going to live another 5 billion years, a total lifespan of nearly uh, 9.5 to 10 billion years. So it will live 10 times lesser because it's gonna burn its fuel thousands of times faster, and therefore it will die in a few million years. Conversely, a tiny red dwarf star, which is much smaller than our own sun, it will sip its mass so slowly that it can, burn till trillions of years, much longer than even our sun. So this is a great insight into the lifespan of a star. uh, I hope our sun doesn't extinguish before its entire lifespan, because then we will have to find another star and then, you know repopulate around it. But it's a thing that we will have to consider billions of years later. Again, we are going to discuss why ideal gas relations are hold valid for stars. So it is not very simple. I told you about how we consider different small elements and their temperature is not varying too much. Therefore, pressure gradients are also not varying too much, and we have this ideal kind of situation. So stars are, composed of plasma majorly, which behaves primarily like an ideal gas. Because in the vast majority of a star's interior, these ions, these free electrons, these protons, even neutrons, they are so energetic and so widely spread out. Because when they are in a bound state, they are much closer, but when they are away, I mean, for example, an electron is free, it's not bound to its atomic structure, then the space between a proton and electron is much larger. Therefore we see it as a much larger distribution of these ions, and therefore they rarely interact through anything than sometimes brief collisions. Therefore the stars don't really follow Boyle's law directly, because Boyle's law, it requires isothermal conditions, that is, temperature has to be constant inside the entirety of the star. But stars are completely opposite to isothermal, because when the core is millions of kelvins hotter, the surface is only 1,000. So how can it be an isothermal situation? They have massive temperature gradients. So actually stars follow adiabatic or polytropic relations, and as per thermodynamics, we can't really, follow Boyle's law exactly inside a star, and therefore we see the mass luminosity relations and opacity also varying as the mass changes. So we will discuss a little about plasma. What is actually going on inside a plasma, which is how we will understand what is going on inside a star. So inside a star, this matter, it exists almost entirely as plasma, and plasma is considered the fourth state of matter. in this entire field of study, plasma physics, that studies this fourth state of matter, and it is an essential part of stellar physics as well. And it is also used in other branches like semiconductor physics, where now they are making microchips using this high energy UV rays, X-rays, and they are creating a plasma like condition where they are trying to do the lithography. So because of these extreme temperature and pressure conditions inside a star, the gas that we are familiar with on Earth, it undergoes a fundamental transformation. It is not like the gas that we see inside Earth. It is different. What are the different elements inside the interior of a star? What is basically this plasma doing with itself? First is this complete ionization, because the temperatures are so high, the pressures are so high inside the core of a star. Approximately for our sun, it's around 15 million Kelvin. So these atoms cannot, hold on to their electrons. Like we see this particular shape of the atoms and these electron shells around it. It is not then there in the plasma, because at these temperatures, they separate these protons and electrons and totally destroy the atomic structure. So the violent thermal collisions actually strip these electrons away from the atomic nuclei, and instead of neutral atoms, the plasma becomes a chaotic, highly energetic soup of positively charged nuclei, which are mostly protons, lone protons, combination of protons, and helium nuclei, which is formed after fusion, and these negatively charged free electrons. And because there are so many free electrons moving around, Thomson scattering effect comes into play. And it is dominant in massive stars, larger stars, where these ocean of free electrons for photons to collide with is prominent. It also shows, therefore, ideal gas behavior. And we discussed it before. The particles were packed so tightly before this plasma condition, by the electromagnetic forces, that it didn't show the ideal gas behavior. But in a star temperature, therefore, the kinetic energy of particles is so staggeringly high that the particles zip past each other very fast, you know, approximating the speeds of light in near death conditions of the star, and their electromagnetic attraction completely, it goes out of the picture. It cannot pull the electrons back into the atomic structure. So these ions, these free electrons and protons, they bounce off each other occasionally, like perfect tiny billiard balls. It's just a metaphor. So it means we can often use simple ideal gas law to model them, because even in ideal gas law, the collisions are very less, the distances between different particles, different atoms is less. The same is in the case of plasma. So we can somehow, not entirely, approximate the behavior to ideal gas. There is also extreme opacity. So because this stellar plasma is packed with charged particles, it is highly opaque to light. When a photon is created in the stellar core through the nuclear fusion, high energy gamma rays, it can't simply fly out into the space. The photon, what it will do, it will get immediately absorbed, or it will crash into an electron or a proton, and then re-emitted in a random direction, which is actually the Thomson scattering. And this Thomson scattering creates process which is called a random walk. Like for example, if it has to go outside the core of the star in a straight line, now it will go like this. It will go zigzag, haphazard, no specific direction. It will be random. What it will do, it will turn into a chaotic motion and lead to an increased time for the light coming out from the star's core to go outside the star's surface and into the interstellar space. And we have discussed this in detail earlier also. So what we see is that because of this dense plasma and this random walk, this single photon that came out from the fusion, it takes anywhere around 10,000 to even 170,000 years to zigzag its way from the core of the star to its surface. So these time scales are also important. That means when the star was was birthing, it the first light to come out of it might have taken this many years. So it might have been a non-glowing star, or a dimly lit star before it started radiating these photons away. Also, these photons lose their energy due to scattering and absorption, and the photons that come out of the star are much less uh, you know they have much less energy uh, compared to the photon that came out from the core initially. Magnetohydrodynamics, I somehow talked about it a few half an hour back, I guess, in this lecture. So because this plasma is composed of moving electrical charges, these free electrons are moving around. Free electrons, that means these negatively charged electrons and these positively charged electrons are moving around. What it does is that it creates its own magnetic fields. These fields that you see outside a star, they are not stable fields. They keep changing because of the convective motion of the star's interior. So they keep changing, and therefore we have the solar storms also. The plasma's movement is physically guided and restricted by these same magnetic fields. These magnetic fields will restrict the plasma's movement also. So interaction between fluid dynamics and electromagnetism is called as magnetohydrodynamics, and it is also an important field of study when we deal with stellar physics. So as this plasma moves around, it churns and boils and goes inside and comes up in the outer layers of the star, especially the convective zone. What it does, it also twists and tangles the magnetic fields. And if field lines snap and reconnect, what they do, they relieve massive amount of energy, which then create these sunspots that we see in the sun, these solar flares, and the coronal mass ejections that are good and interesting topics for astrophysicists to research upon. And they are still doing that. Even telescopes have been sent into the solar system to study these solar flares and these magnetic field lines. Quantum degeneracy. What is this? So it is an extreme situation. So what happens is that in small stars, if the plasma is compressed too much, and like in a small and aging and dying star, a dead white dwarf star, classical physics breaks down completely, and we have quantum physics and quantum mechanics taking over. So we had this guy by the name of Wolfgang Pauli. He gave us the Pauli exclusion principle, which states that no two electrons, remember, no two electrons can occupy the exact same quantum state. What he meant by that, they cannot have the same spin in the same orbital, they cannot exist in certain quantum states, so that it prevents them from being compressed into single space. But when plasma is crushed to millions of grams per cubic centimeter, these electrons are actually packed so tightly that they run out of available quantum slots. So this is an important line, that what happens is that when plasma is crushed to millions of grams per cubic centimeter, at the end stage of the star, the electrons are packed very tightly and there is no space for them, and the Pauli exclusion principle, it denies them to stay in a place where the constant quantum states are exactly similar. So to avoid occupying the same state, according to Pauli exclusion principle, they are forced to move at incredibly high velocities, generating a massive outward push called the electron degeneracy pressure. Now they will have to do it. Like if you try to, you see that sometimes when you compress something, for example, you take a hammer and you take a nail or something and you bang it on the hammer on the surface of that thing. Do it for half a minute or a minute and then touch the object. You will see that its temperature, it has become a bit hotter. It is the same with these electrons, because they are being compressed, they start to move very fast, and actually temperature is a result of the greater kinetic motion of the constituent particles. Therefore, this electron degeneracy pressure takes charge, and this pressure is entirely independent of temperature, and this is what keeps a white dwarf from collapsing into a black hole. So you can see here that how hydrostatic equilibrium has completely changed in this particular case. We now have the electron degeneracy pressure rather than the radiation and gas pressure that is opposing the inward pull of the gravity. So in a white dwarf star, these electrons are forced to be in their lowest energy state. So this resultant electron degeneracy pressure is what supports against the further collapse from the gravitational pull of the star's core. So now here we will discuss the Chandrasekhar limit that I said I will be discussing a few moments later. So we see that there is limit in nature. You have the Eddington luminosity limit, that there can be a limit to luminosity, otherwise the star will explode. Even considering the Pauli exclusion principle, which is an entirely quantum principle, nature has another limit, because it says that the electrons cannot stay in the same quantum state. Therefore, we cannot also compress the star, indefinitely, continuously, and infinitely. It is not possible, because these electrons, they cannot stay, you know, they cannot stay together in the same quantum state. So we have another limit, which comes out as a result of these limits, and trying to define where things will go if we try to uh, you know go beyond these limits. So the Chandrasekhar limit is the maximum mass that a stable white dwarf star can have. If a white dwarf star exceeds this limit, what will happen, that it will not be able to support itself against gravity and will collapse. Mathematically, this limit comes out to be approximately 1.44 times the solar mass. Now we have to understand this limit in a good manner, have a deep insight about it. So we have to understand two forces that are prominent inside a dead star or inside a dying star. They are gravity and the electron degeneracy pressure, as I showed you in the previous slide. So what happens is more mass keeps adding to a white dwarf due to gravity, because gravity will always try to attract more mass, and gravity is getting stronger also because more mass is coming in. So these electrons, they have to move faster. As I told you, the more they will keep moving faster until they don't have any room to do that. So they will keep moving faster and faster to create enough pressure to balance out the gravitational pull. And as soon as the mass approaches this Chandrasekhar limit, the electrons will be forced to move at relativistic speeds, that is approaching the speed of light. Now I am going to talk about another limit that nature has imposed on the universe. It is the limit of light, which comes out from the Maxwell's equations, that electromagnetic waves have the maximum speed limit, which is the speed of light, and nothing can move faster than it. Now, if electrons keep moving faster and faster, they will have to stop because there is a limit. They cannot move faster than the speed of light. So, as they are forced to move at speeds approaching this limit, the speed of light limit, they will stop or something strange will happen. The pressure now cannot win against the gravity. Simple. The electrons can't move beyond the cosmic speed limit, therefore, the gravity will win. And what it will do? It will attract the gas more and more. So, in a white dwarf star, in a binary system, now the mass is not coming from somewhere, there are no gas clouds. It happens when there is a binary system, like for example, there is a white dwarf star and there is a star next to it, and the white dwarf star is pulling mass, and that is in the form of gas from this companion star, and it finally goes over the limit. So what happens? Type 1a supernova will happen. It's an explosion. The star's temperature will skyrocket and it will trigger a runaway nuclear fusion reaction, and it will completely obliterate the star in a massive explosion. What remains after type 1a supernova? It is a neutron star or it can be a black hole. If the core collapse is a part of a massive star's death, if it is a big star and the remaining mass is above Chandrasekhar limit and roughly below 3 times the solar mass, it will collapse further into a neutron star. But if it is beyond that, it will become a black hole. So these are some results, and these results are also important for your own study, and you should also research more about why these neutron and black hole limits come. How do they come? For a standard white dwarf star, the Chandrasekhar limit is given as follows. This is the reduced Planck constant h prime times the speed of light divided by gravitational constant raised to the power 3 by 2 divided by multiplied by the inverse of the mass of the proton squared, which comes out to be 2.765 into 10 to the power 30 kilograms, which is roughly 1.44 times the solar mass. MP is the mass of the proton. So this is an important relation. And how did we Chandrasekhar came to this equation? He came. There's a story about him that he was a 19-year-old kid, and he was in an aeroplane when he discovered this relation. So many Indians don't know about him, unfortunately, but he was a monumental figure in astrophysics and even in black hole physics also, because Chandrasekhar limit is something that determines what will happen when electron degeneracy pressure fails against the gravity. So we are going to derive Chandrasekhar limit here. So to derive the Chandrasekhar limit, we look for a point where this white dwarf star can no longer sustain itself against its self-gravity. This limit occurs when the star's electrons become ultra-relativistic, that means approaching the speed of light. So we are going to look for the point where the gravitational potential energy and the internal kinetic energy of the electrons are going to become equal. So gravitational potential energy is given by this relation gm square by r, where m is the mass of the star and r is the radius of the star. And this is what is holding this is the energy that is holding the star together. It is the gravitational potential energy of the star. Uh, then we have the number of particles n inside the white dwarf, and we are going to focus on the white dwarf star here. So white dwarf star is made of atoms, but this pressure is coming primarily and majorly from these electrons. Since stars are electrically neutral, there is roughly one proton for every electron. Okay, because plus and minus will amount to no charge. Therefore, if we have certain number of electrons, there will be an equal number of protons or nucleons, which is a combination of neutrons and protons. Therefore, there will be the mass will be primarily from the protons, because the mass of the free electron is also very less. So we get the number of particles to be total mass of the star, of the white dwarf star, divided by the mass of a proton, a single proton. Kinetic energy per electron, that the kinetic energy that a single electron has. So we have to first discuss the Heisenberg uncertainty principle. What it states that if you want to calculate the momentum of a subatomic particle uh, through experiments, we will lose information about its position. So we have this relation where squeezing an electron into a small space, that what we are doing when we are compressing and making the electrons to move faster and faster to create the electron degeneracy pressure, we are squeezing each electron into a small space, which gives it a large momentum because of the Heisenberg uncertainty principle. Therefore, we get this relation. We have this relation. And in a star of radius with n electrons, there are n electrons and the star's radius is r, the average space for each electron will be simply delta x is proportional to close to r divided by n raised to the power 1 by 3. How did this come to be? Volume occupied by a single electron will be divided by the volume of the star divided by the number of electrons, which is simply the volume of the star is proportional to r cubed. Therefore, the volume occupied by the electron will be proportional to r cubed by n. Now, uh, if each electron is in a tiny box or cell of volume v electron, the side length of that box represents the average distance between the electrons or the uncertainty in position. And since volume is a cube of this length, therefore we get the cube root of this, we will have r upon n to the power 1 by 3. Now substituting this in the Heisenberg uncertainty relation, which in the Heisenberg, what the I am Sorry for this mistake. I was trying to make a good arrow but couldn't do it. Leave it. I'm not doing it. I need to buy a good device now, I think. So the momentum will come out to be this. The reduced Planck constant times the number of particles raised to the power 1 by 3 divided by the radius of the star. After doing more additions like these electrons are relativistic and therefore their energy is equal to their momentum times the speed of light, we get the energy of a single electron, the kinetic energy of a single electron to be this. Now we have n number of electrons, so we multiply this by n. So we get this n raised to the power 4 by 3. It was earlier 1 by 3 plus 1, which will give n raised to power 4 by 3. Now we will compare this with the gravitational potential equation in order for the star to not collapse or the gravity to not win. And we will get the Chandrasekhar mass limit from here, which is an amazing result. Also, we are going to substitute n as the mass of the star divided by the mass of the protons, and we will get a more concise relation, which is a constant basically, which comes out to be 1.44 times the solar mass. Chandrasekhar was a visual genius. He combined quantum physics with stellar physics and with gravitational physics and came up with this. This is how science develops. Different fields come together and the science mixes up and comes a new kind of science. There's one more additional concept before I close this lecture. It is the Tolman-Oppenheimer-Volkoff TOV limit. It's just similar to the Chandrasekhar limit. While the Chandrasekhar limit was the breaking point for a white dwarf star, the TOV limit is that for a neutron star. After the supernova has happened and the neutron star is formed, we will have further degeneracy going on inside the neutron star. A neutron star's core is actually made up of neutrons. So it has a neutron degeneracy pressure that takes over. The TOV limit, what it tells is that it is the absolute maximum mass a neutron star can have before its own gravity overwhelms it, forcing it to collapse into a black hole. So the mass limit is approximately 2.16 and 2.3 solar masses, and the physics is governed by general theory of relativity, the Einstein's general theory of relativity. And in these extremely dense objects, these neutron stars made entirely of neutrons, the immense pressure needed to hold the star up actually has mass energy of its own. Now this pressure that is keeping the star from collapsing, from the gravity winning, the pressure itself has mass energy, like it behaves like mass. But when we go across this TOV limit, the star's pressure, internal pressure, cannot win against gravity, and finally it leads to a runaway collapse and the formation of a singularity and a black hole. So this is how black holes are formed. This is a very simple explanation, but for the earlier lectures I think it is one that can generate an interest. For you to understand it fully, you will have to have the knowledge of GTR, General Theory of Relativity. I hope you stayed with me till the end and enjoyed the lecture. Forgive me for any mistakes that I might have done while delivering this lecture, and I hope you will learn something out of it. And please keep uh, keep your journey with me as I explain more things. They're a bit difficult, but you will enjoy them if you go from, you know, we learn things when we go from down to top. Like we make basic things understand, then we use those things to build a foundation, then we move up the foundation, build more concepts, and this is how we learn things. This is the same with science, this is the same with everything. And I hope in this time and age of artificial intelligence, we will try to learn new things by ourselves and not let machines take over human intellect. They will be much better, I agree. They will be much more sophisticated. They will have much more connections, you know. They can even lead to different science because they can find loopholes and gaps and relations between different fields. But I would say that we should not let it, take over, and we should just use it. But I don't see things going that way. Still, we will keep doing it, we'll keep learning, and we will not let machines think for ourselves. Thank you.